Next, let's look into the one more most important concept under types of types of significant tests, which is degrees of freedom. Degrees of freedom. So, in the documentation and settings from many statistical tests and probability distributions, you will see a reference to degrees of freedom. The concept is applied to statistics calculated from sample data and refers to the number of values free to vary. That's what is degrees of freedom. It's degrees of freedom, it's nothing but the number of values free to vary. For example, if you know the mean for a sample of 10 values, there are 9 degrees of freedom. Once you know, let me write down. Okay, then this is degrees of freedom. In short, we say df. Okay, it's nothing but number of values free to vary. Simple, the most simplest definition for degrees of freedom. Now let's take one example. So we know the mean of 10 values. 10 values is 10 values is equals to something 60. So now there are 9 degrees of freedom. 9 degrees of freedom. Why? Because so that sample consists of 10 values, so that's n is equals to 10. So df is equals to n minus 1. So df is equals to 10 minus 1. So df is equals to obviously 9. So that's where that values that sample has 9 degrees of freedom. So once you know 9 of the sample values, and the 10th can be calculated and is not free to vary. Okay, that's the actual meaning of this degrees of freedom. So there are 9 degrees of freedom means 9 degrees. Okay, 9 df means we know, once you know, let's take, we know only 9 values of the sample. Let this sample consists of, here we know the mean of 10 values. Now this is nothing but a sample with 10 values. Okay, and we know the mean of 10 values also. Once you know the 9 values of the sample, then the 10th can be calculated and it's not free to vary. Correct? It's not free to vary. So that is the reason the degrees of freedom parameter, as applied to many probability distributions, affects the shape of the distribution also. Okay, so the number of degrees of freedom is an input to many statistical tests. For example, degrees of freedom is the name given to the denominator, n-1 denominator seen in the calculations of variance and standard deviation. So why does it matter? When you use a sample to estimate the variance for a population, you will end up with an estimate that is slightly biased downward. If you use the n in the denominator, if you use n minus 1 in the denominator, the estimate will be free of that bias. So that is the reason we use n minus 1 when you calculate the standard deviation of, you call it as a standard error, that's okay. In spite of using the n value, complete value, we use it n minus 1 because when you use a sample to estimate the variance for a population, we will end up with an estimate that is slightly biased downward. If you use n, if you use the n, it would slightly bias downward. If you use n in the denominator, so in spite of that, if you use n minus 1 in the denominator, the estimate will be free from the bias. To make it free from the bias, we use n minus 1. Let me write it down. So normally we use n minus 1 in the denominator for to estimate the sample variance, because if you use n, it will make a bias. So to estimate the estimate, to make the estimate free from the bias, we use n minus 1 in the denominator. Okay, so that's what the story behind using n minus 1. So let's get back. So as we have discussed earlier, so degrees of freedom is a statistical concept that refers to the number of independent observations or parameters in a sample or a system, and it represents the number of values that are free to vary in a statistical calculation. In a statistical calculation, always remember, it's pretty simple. So when you calculate the mean, if you want to calculate some value from the mean, at least one value would be rigid, one value would be fixed. So that is the reason we have to take out one value when you calculate the degrees of freedom. So represents the number of values that are free to vary in a statistical calculation or model. Obviously we'll have a 9 if it is 10 total number of values. So 10 minus 1 is our degrees of freedom. In the context of hypothesis testing, degrees of freedom are used in calculating test statistics such as the t-test and the f-test. The degrees of freedom for a test depend on the sample size and the number of parameters estimated in the statistical model. For example, in a t-test, for independent samples, the degrees of freedom is calculated as df is equals to n1 plus n2 minus 2. So where n1 and n2 are the sample sizes for two groups being compared. So as we have discussed earlier, n or sample size is nothing but the number of observations, or you can call it as the number of rows in it, or you can say it as number of records in the data. Either number of observations, total number of observations, or total number of rows, or total number of records. And degrees of freedom, df, is the notion or notation is used to identify the degrees of freedom or represent the degrees of freedom. So now the degrees of freedom represents the number of observations that are free to vary in the calculation of the t statistic. So after accounting for the estimated parameters in the model. So similarly, in an analysis of variance ANOVA test, the degrees of freedom are calculated based on the number of groups being compared and the total sample size. So the degrees of freedom for the between groups variation is equal to the number of groups minus 1. So while the degrees of freedom for the within group, variation is equal to the total sample size minus the number of groups. So that's what we use it in analysis of variance, ANOVA. There are two measurements of degrees of freedom in ANOVA. So DF in ANOVA. That's one is degrees of freedom, DF, for the between groups. That formula anyway is we have given there. So between group variation is equal to the number of groups. So is equal to the variation is equal to the number of groups minus 1. Okay. So number of groups minus 1. This is specific to the ANOVA. And DF in DF within DF for within groups is equal to total sample size is equal to the total sample size of the group minus the number of groups. Total sample, because it's within a single group, total sample size of the group minus total number of groups. So that's what DF in ANOVA. So in general, degrees of freedom play an important role in statistical inference, as they affect the precision and accuracy of test statistics and confidence intervals. A higher number of degrees of freedom generally leads to greater statistical power and narrower confidence intervals.